So in this and upcoming videos, what we are going to be trying to develop is a more general theory of integration. So the theory of Riemann integration works on the real line, and it can be extended. You know, it's not too difficult to imagine ways to extend it onto R2 and R3 when you've got the scalar functions on those. And it can be done, but we are going to study a more advanced theory of integration, which can be equipped onto much more abstract structures than just the real line and vector spaces over the real line. And what we're going to do is we're going to then develop an abstract theory of integration on all of these spaces, and then we're going to see how Lebesgue integration is just this theory of integration applied to the real line. Before we can get into the meat of integration, we need to firstly see the abstract structure that a set needs to have in order to be able to put a theory of integration on it. Okay, so the structure that you need to have is something called a measure space. A measure space. Okay. So, what is a measure space? So in this video we're going to define what a measure space is, and it's not a ridiculously easy concept. So firstly, the first thing is nice and easy. You start with a set. With a set of elements which we'll call X. A set of elements X. Okay, you then need something called a sigma algebra of subsets of this set X. So, hopefully you know what the power set of X is. The power set of X is just the set containing every possible subset of X. So it's basically the set containing E, which is a subset of X. And that's what it is. So a sigma algebra, given this curly S shape like this, is a subset of the power set of X. So it's a collection of subsets of X, and it has to obey some axioms. Firstly, and this is all based upon probability spaces. So these axioms should be familiar from probability. So firstly, this set would be the set of events. The set of events forms a sigma algebra. So firstly, phi, the empty set, and the whole set are elements of the sigma algebra. So no surprises there. Again, a topology is a subset of the power set, and this axiom is the same as in topology. We want the whole space and the empty set to be in there. Okay, 2. This one certainly isn't in topology. If E is an element of S, then it needs to imply that E complement is also an element of S. So whatever set you have, the complement also has to be in there. And think of them in terms of probability. This means that if you have an event set which is E, then another event is the event that event doesn't happen, i.e. the complement of it. So in probability, the set would be the sample space, all possible outcomes of an experiment, and the sigma algebra would be the set of events. The work would be it would be the set of events, and an event is a subset of the possible outcomes. If E is an event, then the event that event doesn't happen, which is all the outcomes that are in E complement that aren't in E, that would be also an event. So that's an intuitive property from probability. And an event is just something that you can ascribe a probability to. For instance, I don't know why I'm going into probability spaces so much here, but it is the intuitive way of defining what a measure space is, and what's so brilliant is that the definition from this abstract branch of analysis mirrors the definition that came from probability. So for instance, if our set of outcomes, which is our set X, is all possible points that I could select out of the interval 0 to 1, then the set of outcomes would be, this interval 0 to 1. But an event would not be, for instance, me getting 0 would not be an event. because you cannot ascribe a probability to that. What is the probability that I choose 0? You can't ascribe a probability to that because it's so close to 0 that you can't do it, because you've got an uncountably infinite number of points in here. So events have to be intervals in here which have an actual probability that you can ascribe to them. So that's why it's not trivial that it's not the case that this is always the power set, for instance. But if E is an event, so if this interval is an event, then the event that I don't get that, I get its complement, which is all these points here, is an event as well. So E complement is also an element of S. And then again, another property that mirrors probability is that if En are elements of S, then the countable union, the countable union n is equal to 1 to infinity of En is also an element of S. So if you've got a countable number of events, then if you union them all together, that will also be an event which you can ascribe a probability to. So those are the axioms of a sigma algebra, and if you ever forget those, just think of probability, because they are so intuitive when you think in terms of probability. You could make this really abstract. You could make it, definitions, just like from topology, where it does seem very, very abstract when you first see the definitions of a topological space. But if you think in terms of probability spaces, those are all very intuitive axioms to have obeying. So think of this aspect of measure spaces as coming from probability. Okay, so that's what a sigma algebra is. So a measure space is this set with this sigma algebra, in the same way we write, the topology tau, or fancy U for the set of open sets. Here is I'll just write it up here. Sometimes you write curly U like that, or sometimes you see just tau. These are topological spaces where you have the set, and then you have this set of subsets, which is the topology, but that's not relevant at the moment. But it's a very similar concept to that. But you have one more thing in a measure space. You have something called a measure, which is mu. Mu is a map which maps all the subsets of the sigma algebra onto the positive extended real numbers, or rather the non-negative extended real numbers, because it includes 0. So plus infinity is an option. You can send a set to plus infinity, because this is the extended real numbers. You can send a set to 0. You can send a set to any number in between, but you send the sigma algebra. So every sigma algebra has a number ascribed to it. Now, if this was probability, we would just have 0 to 1. So every event would have a number ascribed to it between 0 and 1. This is measure theory, however, so you can go up to infinity as far as we're concerned. You do not have sets that we ascribe a negative measure to. Think of this as the sort of size of the subset. So you can think of, for instance, this was created to be analogous to, for instance, the properties of area. So if you have like a plane, I know there's things like exterior algebra to rigorotize the concept of areas and volumes and things, but this is one way of doing it. You have this is a subset, for instance, so the plane would be our set X. This set here would be in our sigma algebra over here, and then we could ascribe a number to it through the function which would be our measure, which in this case would be area, and that would ascribe a number to it. So think of measure spaces as really being a generalization of the concepts of length, area, volume. It's ascribing sizes to subsets of our set. And it has to obey some axioms. So the intuitive axioms, firstly, it only has to obey 2. That mu of the empty set is obviously 0, because the size of the empty set should be 0. 2, that if you have A, which is the disjoint union, I is equal to 1 to infinity of AI. So for instance, if this is our set A is an element of the sigma algebra, then if it is the disjoint union of a countable number of other sets, so these are all A1, A2, A3, all the way up to a countable number of them, so it goes on and on, but they are all disjoint, meaning that there is no overlap. So this and this would not be disjoint, but these sets that make it up are all disjoint. There's no intersection. So AI intersection AJ is equal to the empty set if I is not equal to J. So if A is equal to this disjoint union, which is what this square union sign means, if it's equal to this disjoint union of AI, where AI are all elements of the sigma algebra, so you can ascribe a number to them, so they've got a measure, then the size of A is what you think it should be. It's the sum of all the sizes of the other bits. Now, of course, there might be an infinite number. If it's finite, then of course it's just the sum. If it's infinite, if it's countably infinite, then you need to take the limit. It's the limit of the partial sum. So we know how that's defined from real analysis. We know how to do that. I'm assuming you know how to do that. Okay, so those are the axioms, basically. This is called countable additivity. And those are all the axioms of a measure space. So you have a set. You have a collection of subsets of that set, and you have a function which ascribes a size to each of the subsets that are in the sigma algebra, S. So that is the concept of a measure space. So I'm going to end the video there. In the next video, I don't know what we're going to do yet. I want to get onto the concept of integration pretty quickly. I want to show you how this can be used to define a notion of integration. But before we can do that, we're going to have to go over some pretty difficult things, such as the concept of a measurable function, which is really just a generalization. It's so analogous, completely analogous to the concept of continuity in topological spaces, but it still is it's a new concept, and we also need to define, in fact we'll do in this video, we'll show how the real numbers is a measure space in this video. Okay, so let's do the real numbers as a measure space, the real line as a measure space. Okay, so well, firstly I start off with the set of real numbers. So I've just got the set of every single real number is the start. I want now a sigma algebra. So how am I going to get a sigma algebra? Well, basically there are lots of different sigma algebras of subsets of the real line. One that comes up again and again and again and again is something called the Borel sigma algebra of the real line, given this fancy curly B, R. There is another one that's going to become very important later, but is much, much more difficult to understand what it is, called the Lebesgue, the set of Lebesgue measurable sets of the real line. That's far more complicated, and we'll have to go over that much, much later. It's very, very important. It's bigger than this set, but it's far less easy to understand, and you have something called the length function as well, which is the measure. So I'll show you what those concepts are. So so the real line has our familiar topology. So we're looking at the real line as a topological space now. You have this subset of sets. This is called a topology, which is, again, I prefer the big curly U to the tau, is a subset of the power set of the real line. And it obeys some axioms. It obeys the fact that phi and the whole space, which in this case is the real line, are elements of it. It obeys the fact that E1 and E2 are elements of U. That implies E1 intersection E2 is an element of U. And the final one it obeys is that if E alpha rather are elements of U, then the arbitrary union, it doesn't necessarily have to be countable, it could be uncountable, of open sets is also open. So those are the axioms that the topology obeys. So the topology is another subset of of the real. It's another set of subsets of the real line. So it's a subset of the power set of the real line. And basically, the Borel sigma algebra, the real line, is basically the smallest sigma algebra that contains all of the open sets, that contains all of U. So it's given this symbol, the sigma algebra generated by U. So basically, the way you can define this is it's the intersection of all sigma algebras which contain U. So U, so if we put I I don't know how many there are, so I should put alpha, such that U is a subset of the sigma algebra alpha. So it's the intersection of all of these, that's what it is. And you can prove that that is a sigma algebra. Shall we do that? Yes, we'll prove that it's a sigma algebra, that it exists. So I prove to you that it exists. I'm not going to prove to you, I'm not going to show you what it is, because it's quite complicated what it actually is. But it does exist, this sigma algebra with the open sets sitting inside of them, and that gives you a good picture of what it is, because we know what the open sets are. So the Borel sigma algebra has all of these open sets inside of it. It has a few more sets as well, so it has everything that you could possibly get by, for instance, taking complements. So all complements of open sets will be in there, so all the closed sets will be in there. It will also have, you know, sorry, I'm looking at the axioms of the topology rather than the sigma algebra, but you know it'll be closed under because it's closed under complements, it will imply that it's closed under countable intersections, because if it's closed under countable unions, then it will be closed also under countable intersections. So intersections of open sets will be in the sigma algebra, and we know of course that you can intersect open intervals to get down to a single point, so all the singletons will be in our Borel set of the sigma algebra. So it gives us a good picture of what the Borel sigma algebra is. So I'm going to prove to you that the intersection of all of these sigma algebras which contain U is also a sigma algebra. So firstly, what's the first axiom of a sigma algebra? Well, firstly is that phi and the whole space need to be elements of this sigma algebra. Well, because every single one of these is a sigma algebra, that implies that phi and the real numbers are elements of the sigma algebra of alpha for all alpha, which implies that the intersection alpha S alpha has as elements phi and r, because it's in all of them, therefore in the intersection of all of them will be these two elements. So that's property 1 done. Property 2, what is property 2? Okay, property 2 is that if E is an element of this intersection, that needs to imply that E complement is an element of this intersection alpha. Yes, alpha. Oh, firstly, I should have just said, if it's an element of, if U is a subset of all of these, then it's pretty obvious, I hope, that U is a subset of the intersection of all of them. So we know it's non-empty. It contains something. It contains at least all the open sets. So it was pretty trivially obvious that this was true from the beginning, because they were elements of the topology. So that argument wasn't even necessary. You could have got it from here. Okay, so E complement. We want to show that E complement is an element of here. Well, if E is an element of the intersection of alpha S alpha, then that implies that E is an element of S alpha for all alpha. Now, because these are all sigma algebras, that implies that E complement is an element of S alpha for all alpha, which implies that E complement is an element of the intersection alpha S alpha. Okay, that was nice. And then the final one, we want to prove that it's closed under countable unions. And again, we're going to follow the exact same routine as we've done here. We're going to say if it's in this, then it's true for absolutely all of them. Because they're all sigma algebras, then and then it's all in because all of them, yeah. That's what we're going to do, basically. So, let E be equal to union n is equal to 1 to infinity En. Okay, and En are all in the sigma algebras. We want to show E is an element of the. Oh no, Ens are elements of this intersection. N is the. Oh dear, used are the same. Turn this into an M. Turn this into an M. M. The intersection M is equal to 1. Oh no, sorry, I didn't even need to do that because it's over alpha. Sorry. Let me continue. Let me just find where I was. Okay, so EMs are all elements of this intersection. We want to show that E is an element of this intersection. I should have called this intersection a name, rather than having to write intersection continuously. Okay, so if EMs are all elements of the intersection alpha S alpha, then that implies that EM is an element of S alpha for all alpha and for all m. Therefore, that implies that because they are all sigma algebras, then the union m is equal to 1 to infinity em is an element of S alpha for all alpha. Bingo. Which implies that union m is equal to 1 to infinity em is an element of the intersection S alpha. Oh, I've forgotten the curly bits. S alpha over alpha. Okay, that is your proof that this sigma algebra exists. That if I intersect all sigma algebras which contain the open sets, then I'll get another sigma algebra, and it will be smaller than any other sigma algebra which contains the open sets. So how do I know that there even is a sigma algebra that contains the open sets? Well, here's the clever thing. The power set of R contains the open sets, and the power set of R you will find obeys all the axioms of a sigma algebra. So there is at least one sigma algebra which contains all open sets. So if that's the only one, then indeed that will be the sigma algebra generated by the open sets. Of course it's not. So there is a much smaller algebra containing the open sets. It exists, it's the smallest one, that's what this proof shows, and that, if you can find it, is what the Borel sigma algebra is. So basically, if you want to get a flavour for what the Borel sigma algebra is, as I've said before, it contains all open sets and it obeys the axioms of a sigma algebra. So any set that you can construct from the open sets plus the axioms of the sigma algebra is going to be a Borel set. So that is a sigma algebra on the real line, and that's going to be very, very important when we come to define notions of measurable functions.